Great. Okay. Well, it's a tremendous pleasure to be able to introduce Paul to my colleagues here at UBC. Um, I had the honor of spending the first 10 years of my postgraduate career at NRC just down the hall from Paul. And even as a fresh postdoc, it didn't take long to realize that Paul was really a very special scientist. Um, he did his PhD in pure theory, I think stat mech area, right, Paul?
That's right. Yeah, that's right.
Um, but there he was at NRC in a plasma physics group building state of the art new lasers and developing visionary schemes for doing time resolved dynamical studies of molecular motion. Um, so it was always very inspiring to talk with Paul at every opportunity. And to put things into context for my condensed matter colleagues who will know Alan McDonald, Alan was also at NRC at that time. And I noticed two things which have stuck with me ever since. Um, Paul and Alan share an uncanny ability to, when you're sitting down discussing a problem that is mysterious to me, I don't know where to start, they can both immediately get to the essence of the problem and then help solve it in a purely linear, systematic fashion that incorporates great insight and heuristic concepts from the beginning to end. And the other thing that they share in common is they're both from the Maritimes. So I'll let you guys do the statistics on that. But um, so it was absolutely no surprise to me that Paul has gone on to become one of Canada's most honored scientists for work that is associated with this talk today. And I can also finish off by maybe putting this in context for a broader spectrum of colleagues in the department from a number of different fields. Paul's won a large number of prestigious awards internationally. I'm not going to list them all, but for context, I'll just cite some of the other people who have won the Institute of Physics Isaac Newton Medal and Prize, which Paul won last year, or 2019. And so other recipients of that include Charles Bennett, Martin Rees, Leo Kanoff, Ed Witten, and Anton Zeilinger. So that pretty well covers the bases, I think. And so interacting with Paul while I was at NRC was what I missed most when I left NRC. But it's been a great pleasure for me following his amazing contributions to basic scientific knowledge. So thank you, Paul, for presenting this talk to us today.
Well, thank you very much for this very nice introduction. And well, I remember those times as well in M23A. I put on my introductory slide, which I noticed I gave the different title than the title I gave to you before. I put a picture of the Joint Attosecond Science Lab, partly at NRC on the left and at University of Ottawa at the right in these two buildings. But the building that Jeff and I shared with other people as well, it's really where all laser work was at that time, was a sort of a dilapidated, rundown building at on the Montreal Road campus out in the suburbs of Ottawa. But the people that worked there were amazing, amazing scientists, and many of them have gone on to do great things, Jeff included. And so a dilapidated building doesn't always mean dilapidated work. The building here, the Sussex Drive building of NRC, is where my lab is now. And that's on the left. You can see the Ottawa River behind it. It's a beautiful location. So 2 houses away from the Prime Minister's residence. So from my office, I get as good a view as the Prime Minister would get from, I don't know, his bedroom or whatever is facing the river. It's a beautiful view. And so I was just saying that I was down a couple of days ago and the ice was still in the Ottawa River. It wasn't blue like what you see here. It was still covered with ice, but I suspect it's no longer covered with ice. The University of Ottawa built a new building, the Advanced Research Complex, about 5, maybe 7 or 8 years ago. And that's the one on the right. It's also a beautiful building, but it somehow lacks the grandeur of the NRC building. I don't know if everybody knows it, but before I go on, I'll mention something about the building. If you look at it closely, you might have seen it before because it's modeled on Buckingham Palace. It's not exactly the same as Buckingham Palace, but go find a picture afterwards of Buckingham Palace, and you will see that it's very, very similar. And I believe that it was truly modeled on Buckingham Palace. So Canada was truly a colony in the time this was built, which is 1920. Now I looked on the website before I prepared my talk, and it said the talk was for undergraduates, partially. And so I decided that I would put a few things in just to make sure that everybody was on the same page. So I don't know how many undergraduates came, I can't see. But I thought I would start out with what is an attosecond, because I come from the Giant Attosecond Science lab. So an attosecond is 10 to the minus 18 seconds, or 1 over 1 with 18 zeros. I like to say you divide a second into a million pieces and you get a microsecond. You divide a microsecond into a million pieces and you get a picosecond. And you divide a picosecond into a million pieces and you get an attosecond. It's nice to contrast it with there's no easy contrast in time and space, but maybe you'd say a meter is like a second. So if you do, nanometers, which is a big thing, nanometer science, is 10 to the minus 9 meters, which is huge compared to attosecond to a second. Even a nuclear diameter, which is about 10 to the minus 14 meters, is larger compared to a meter than an attosecond is compared to a second. And a proton diameter is, say, 10 to the minus 15 is still way larger. So an attosecond is really, really, really short. So since we're talking about attoseconds, and I want to end up with multi-electron dynamics, let's look and try to think about what you might expect to happen on an attosecond timescale. So I picked this off the web, and it sort of talks about the natural timescales for gases, really. So an air molecule collides with another air molecule about once every nanosecond. So nanoseconds would be a typical time for collisions in densities of air and temperatures of air. A molecule will rotate, a typical molecule will rotate in more or less a picosecond. Of course, there are big molecules which are slow, and there are smaller molecules which are relatively fast, but sort of picosecond-ish. A chemical reaction cannot be faster than moving the atoms apart, you might say. In other words, chemistry is really moving atoms. And so it really can't be much faster than a femtosecond just because of the inertia of pulling the atoms apart. So attoseconds is the electron timescale. Electrons move and interact on the attosecond timescale. And so that's the kind of physics that will be opened up with attoseconds. In a way, if you wish to make an attosecond pulse, you must deal with electrons. So I called this, I think I called it when I put the advertisement in for this, Attosecond Science. But I sometimes call such talks using light to control electrons, which in turn controls new light. This is much more general than what we do in attoseconds, but it's a good way to introduce attoseconds. So think of an atom, which is illustrated here, and think of electrons in the atom, illustrated right here as classical particles. Of course, you all know they're not. And think of an intense laser field or a laser oscillation. I'll simply follow one cycle of that oscillation. And when the laser field is strong enough, then the pull on the electron is great enough that the electron will emerge from the atom and go into the continuum. So it will come out somewhere near the peak of the field. If you want to think of it quantum mechanically, the electron you can think of as tunnels. But if you want to think of it classically, you're just pulling and eventually you pull stronger than the ion pulls back. Once free, the electron gains momentum in the presence of this relatively intense light field, pulling away from the ion from which it originated, gaining momentum, and that momentum pushes it uphill against the field, which now is pointing backwards. And depending on its moment of birth, in this phase back here, its moment of birth, it can come back and collide with the ion from which it left. The illustration shows one electron hitting another and knocking it free, and this happens. But what is really driven attosecond science is something a little different. The electron comes back and falls back in and is captured into the state from which it left, giving off its light as a photon, giving off its energy rather as light as a photon. You might think of this classically as the electron, which is being driven by the laser field at the frequency of the laser field, sees the Coulomb potential, falls in and out, and has a high frequency emission. And that would be a classical analog to what really happens quantum mechanically, which is the electron recombines. This process that I've talked to you about, which seems so classical and so simple and things like that, can be made quantum mechanical, but I will do it a little later on, but it will still be simple. And it happens pretty well in all materials under strong fields. I might state this in semiconductor or solid state language, just because I know a lot of people are in solid state. And we can transfer it into solid state, and much the same process happens. So let me say it in solid state language, where we have energy and momentum. An electron is created by a band-to-band transition from the ion, which has a very large mass, and therefore has essentially energy versus momentum, which is flat, up to electron, which has a much lower mass, and has an energy versus momentum, which is parabolic. The electron now is accelerated on its band, its parabolic band, until the electron and ion find each other, which is not now illustrated in this illustration. And then they make a transition back to the ground state from which it left. The electron and ion recombine, giving off radiation as a photon. That's just the same thing as I've talked about over here, but I'm talking about it in solid state language. And indeed, exactly this process happens in a solid. But I won't talk about solids here. I'm really talking only about atoms and molecules. So just to make sure that that's absolutely clear to you, a moment of birth, illustrated here by a moment of birth in the field, is mapped into a moment of recollision by F equals ma and an energy of recollision. I illustrate by red, green, and blue, and I've illustrated that by some arbitrary number. It depends on the field and the wavelength, but the recolliding electron could easily be 100 electron volts of energy when it recollides back with its parent ion. And if it's 100 electron volts of energy in this trajectory, if it was born a little bit later, it will have a lower kinetic energy, 50 electron volts, let's say. Again, this is arbitrary, I made it up, but this is the way it works. And it's still later birth will lead to an earlier recollision and a lower energy. So we have a sweep of energy from red to green to blue, a bit like taking a short pulse through a material, and the material will disperse it. So if I take a short pulse through tin, especially of this wavelength, it will be dispersed. And what I'm doing is just doing the opposite. I'm taking the red, the green, the blue, and I put it through tin, and I make it back again. So this process that I've described to you earlier produces a chirped pulse, red, green, blue, and when you pass it through a dispersive material, in this case tin, remember it's UV, so solids can be transparent or relatively transparent to this material, to this radiation. You can create an attosecond pulse. And indeed, this is exactly how attosecond pulses are created, even the tin. Now, I don't know, again, if any undergraduates really turned out. I can't see anybody here, so I don't know. I don't know if any undergraduates came, but if you did, I want to give you an assignment. So consider an electron born with zero velocity at any phase. That's what I've described to you, more or less to begin with. Electron born with zero velocity at any phase. Use F equals ma. Let's assume an intensity or a field. I'll make it 3 volts per angstrom. That's sort of a typical field. That would be an intensity of 10 to the 14 watts per square centimeter. And I'll have a moment of birth. Let's call it T ionization. And we'll put T ionization at any phase you want between 0 and 180 degrees. It'll replicate itself after that. You can go through a pulse, but you don't have to if you don't want. And calculate if there will be some phases and there will be some phases will not recollide, when it will recollide if it recollides, and with what kinetic energy. The electron returns to the origin. You may ignore the Coulomb potential after the birth. That's called the strong field approximation. And if the laser field is strong enough, that's not a bad approximation. And you will get what I've told you before, and you'll just know it. It'll be in your fingers and you remember it forever. You will have calculated the chirp of the pulse. This is the recollision energy as a function of time, or the time-dependent photon energy minus IP. And that would be exactly what you would see, or almost exactly, but qualitatively what you'd see in the experiment. If you add the probability of birth given by tunneling, which is 1930s quantum mechanics, then you have almost everything. And the paper describing this, Classical Physics and Tunneling, was published in PRL. Can you imagine the PRL would take a paper based on classical physics in 1993? It's a long time ago, but still. So how does one make a short pulse, an attosecond pulse, really in practice? So, well, it's controlling light to control the electron to make new light. So controlling light, we'll make a time-dependent laser pulse who is perfectly controlled. And the simplest way to think of it is, let's make a pulse that's only a cycle or a cycle and a half long. Over here on the right-hand side, you see the square of a time-dependent field of a pulse that we can produce, which is even less than a cycle long. It's even half a cycle long. So that can be done, and people can make pulses that are a cycle or a few cycles long. Now let's think about it. Here, the intensity isn't strong enough to remove an electron. Let's make it so the intensity is also not strong enough to remove an electron around this peak. But by this peak, maybe the intensity is strong enough to remove an electron with some probability. The electron is caught in the increasing field, driven away, driven back, and recollides with high energy, creating that burst of radiation that I described to you with all of the descriptions, the chirp and everything is not shown. Now you're going to say, okay, but the next half cycle is even stronger. The atom is more likely to ionize. And so that electron will also be created, or it will have a probability of being created. And it will be pulled away by a strong field. But it will be driven back by an increasingly weakening field. And it will come back, and maybe it will recollide, but it will recollide with much lower energy, and therefore give a much less high frequency burst of radiation. So looking through a filter, And just looking at the highest frequencies, one gets an isolated attosecond pulse that's chirped, and we put it through a material like tin to fix it. But otherwise, that's it. So what's down here is just the equation for what energy you can get, and it depends upon the field that you're pulling it away with, or the field that the atom ionizes. It depends on the frequency of the laser that you're driving, and that's really all there is to it. It's really quite a simple thing. So one can drive with 800 nanometer lasers up to around 150 eV. I said 200 eV in a high IP atom like helium. Helium is not ideal, mostly neon is used. And you can go up to high IP at 800 nanometers. And if you want to go up higher to a kilovolt, which people do, people can go to a kilovolt attosecond pulse or kilovolt high harmonics, then you have to push the wavelength of the light longer and longer. And so that's the way. Okay. Now, I have not told you everything. I've only told you as if it's a single atom being irradiated by a beam. I have told you that all of the complexity is out here in the laser, which is not shown. We have to make almost a single cycle pulse if we want an attosecond pulse. But if we take an ordinary garden variety Ti-sapphire laser, we'll have an attosecond pulse followed by an attosecond pulse, followed by another, followed by another. Fourier transform it, it's a series of harmonics. Harmonics 15, 17, 19, 21, 23, 24, etc. And this is the typical harmonics created by a typical femtosecond laser pulse irradiating argon, or maybe neon. This is argon, I'm pretty sure. If I isolate it, as I told you before, here is the spectrum going out further. You can see it not only 35 eV, but it's on the same scale, approximately the same scale, continuously. In the vertical direction, I forgot to say, there was no information. It was just a spectrograph, so you see a spectral line. In this case, it's a reconstruction of the spatial structure of the beam. And so this is telling you about the spatial structure of the attosecond pulse, but roughly it's a continuous spectrum pushing all the way out to well over 100 eV. Okay, so that's high harmonic generation. In reality, it's not very complicated. All the complexity is out here in the laser, and if you want to do this, you can just go buy such a laser, a commercial laser, and put together a vacuum system. A supersonic jet, that's what we use here in Ottawa mostly, but it can be a fiber holding gas, it can be a cell holding gas, and nowadays it can be a dielectric, although you cannot push to such short wavelengths. But you can push to 25 eV using a solid material. So now I've described to you creating an attosecond pulse, and I hope you will not forget it. I don't think you will ever forget it. And if you go through the calculation I asked you to do as undergraduates and you get it, you will have it in your fingertips and you will never forget it. This is such an easy idea. So now let me describe measurement quickly. This is the gold standard of measurement. It's called the attosecond street camera. And it's easiest to describe it by thinking about a conventional street camera, which maybe nobody in the audience here has ever really looked at or thought about. So let me describe a conventional street camera. This is the technology of the 1960s, I guess, or 50s, when it was difficult to make measurements of short light pulses. So you brought a pulse in to be measured into a photocathode. And in the photocathode, the idea is you make a photoelectron replica of the pulse that you wish to see. Now, of course, you make the photoelectrons out of a solid. They got to make their way out of the solid. So the energy is not a perfect replica. They can lose some energy in the process and so on. But you make the best replica you can make on the photocathode. Now you pull the electrons as fast as you can up to between two deflection plates on which you place a high voltage time-dependent field, just like a television, old-fashioned television set. And so the first electrons that come in, they see one field and are deflected over here, And the later electrons that come in see a different field and they're deflected over here. And so you create a streak across a screen, a fluorescent screen, that is a streak showing you the structure of the pulse. That's a streak camera. Streak cameras like that are still used for measuring X-rays, and they've really become improved considerably. I think they can now have a time resolution of less than a picosecond, maybe 100 femtoseconds even, I don't know. But otherwise, except for here and there, they're essentially unused. But you could think about how you could improve such a streak camera. So one problem is the photocathode. So let's get rid of the photocathode. Let's replace the photocathode with an atom. So now I come along, I just ionize, and I create a photoelectron up here. Let's take it the hydrogen atom to make it easy. I create a photoelectron. Its energy range is exactly the energy range of the pulse. Its time structure is the same. As long as I have a simple enough atom, I create a true photoelectron replica of the pulse. So that's the first thing, and that would improve the streak camera dramatically. The second thing is, if you're going to use an atom, why put it over here? Why not stick it right in the middle of the deflection plates? And so we'll put it right in there in the first place. And then why use deflection plates? Why not replace the time-dependent field with an infrared laser pulse? Laser pulse gives you a time-varying field. It's just faster, but that's great. We want to measure an attosecond pulse. And then the last part we generally use, we take the measurement in energy instead of streaking it across a camera, across a fluorescent screen. But that's sort of either way would be fine, I guess. So the attosecond streak camera replaces the photocathode with atom, replaces the time-dependent field with an infrared field from a laser, and that's the deflection. So that's the best way to measure attosecond pulses. In fact, what you measure is something, this is actually how such a measurement goes. So let me talk about that first. This is not from my lab, this is from some other lab. This is from the Kraus lab in Vienna, or in Munich. A short pulse comes in and creates the attosecond pulse. The attosecond pulse now propagates along with the short pulse, and it's separated from the driving pulse by a set of apertures, now creating an infrared beam, which will do the deflection, and the attosecond pulse that comes through here is the UV. And they come to a second jet, a neon jet, and in the neon jet, we do exactly what I told you with the attosecond streak camera, and we measure the energy of the electrons that are created in a time of flight setup. So that's the attosecond streak camera. And so now I think I can sum up this part, the production and creation. So summing up, solving F equals ma, isn't it amazing how simple? The intensity which an atom ionizes, actually I didn't make that case, but you could calculate ionization classically, and you'd be almost exactly right. Because when you tunnel in femtoseconds, it's not much different than classical ionization. So it's the intensity at which an atom ionizes, the frequency and time structure of an attosecond pulse, how attosecond pulses are measured. Isn't it disappointing that classical physics is so good? So let me go on now and talk about a quantum mechanical perspective on exactly the same problem. And you might say, why? But I'm going to show you why in a few minutes, why that might be useful to think of it in the quantum mechanical way. So, of course, now I don't have a classical particle. I have a wave function. So here's a wave function sketched in the Coulomb potential, perturbed by a laser field, so it's tipped a little bit, and the electron tunnels out. Now, I'm going to have to show you sort of one picture that tells you multiple things. So the electron that tunnels out is a wave packet into the continuum. Of course, the wave packet is going to move like I described to you in classical physics. Different colors will arrive at different times, different wavelengths. but they will come back and overlap the ion from which it left, or the electron, the other portion of the electron. So I have two components of the same electron, all coherently related. This creates the wave packet, which now comes back and interferes with itself. So coherence between the light and the recollision electron, and between the recollision electron and the attosecond pulse. I didn't really say how the attosecond pulse is created here, but you might see it already, because think about the interference between the bound electron, shown in the Gaussian, and the recollision electron zooming past this corrugation one on top of the other. The next figure will show it. But I also want to say that this is a well-timed projectile, a quantum mechanical projectile, a portion of the wave function that's hurled back at the ion. And you can think about using it in multiple different ways. Okay, so reading that interferometer, because that's really an interferometer, or creating the attosecond pulse is really illustrated in this illustration. The recollision electron, shown here like a washboard, and the bound electron, you can imagine the Gaussian there, they overlap and they interfere, creating that interference. And that interference, there's a minimum here that overlaps the Gaussian, pulls this down. There's a maximum here that overlaps the Gaussian, pulls that up. Square it, and we find the charges on one side of the atom or molecule. It will be true in solids. And as the wave packet moves forward, where there was once a minimum, now there's a maximum. And where there was once a maximum, there's now a minimum. And so the charge has moved sideways. So we have this oscillating charge as the wave packet moves through, and an oscillating charge emits radiation. The amplitude and phase of the recollision electron are transferred through the light through the transition, the dipole moment, or the transition moment. I just described a dipole moment here and how you get it, but that's the transition moment. From a point of view of a projectile, the electron is a short wavelength projectile. If you think about using a photon of the same energy, it's a much longer wavelength electron projectile. I'm going to use, throughout all of this talk, the electron. And the attosecond pulse is only a way of looking at the electron and knowing about the electron. Okay, so now I've talked about a basic quantum mechanical way to see it, but I hope everybody sees the direct mapping of classical physics into this qualitative quantum mechanical perspective. So, and I told you, and I hope everybody sees that this quantum mechanical perspective is really an interferometer. The bound electron is interfering with that other portion of itself, the electron wave packet that's coming back and overlapping with it. So I want to make a jump here, and I'm going to now leave the technology. But in order to do it, I want to say that we measure E as a function of T, or less often, but we could have done so, E as a function of F, with a sheared nonlinear interferometer. I took a picture off the internet of an autocorrelator. A pulse is brought in, divided in two. The two pieces come back and interfere with one another. And you simply measure this interference in a detector back here as a function of the position of one of these mirrors. You can see these mirrors are moving back and forth. And so as these mirrors back and forth, you get constructive, destructive, constructive, destructive interference, and there's the autocorrelation. And that tells you something about the duration of the pulse. In fact, you can do better than that if you take this from being just a detector to being a spectrograph and look at the spectrum. And if you get the spectrum measured in the same way, then you get FROG, it's frequency resolved optical gating, which allows you to fully reconstruct the time structure and, in principle, although we don't usually do it for space, the spatial structure of the pulse. So you know everything about E as a function of T by interferometry. So by analogy, we can measure the electron wave packet by this kind of interferometry. So I'll let you think about that, because I'm going to go on now and talk about measuring the electron wave packets in two different ways, as long as I have time. Let me keep an eye on the time. And two different ways. One, something we did some years ago, and one we're working on right now. So can we make similar measurements of the wave packets involved? The recollision electron, the bound electron, which could be the molecular orbital, multi-electron dynamics, I'm going to show you that later, and molecular dynamics. I'm not going to bother to, I won't show you that here. So now I'm ready to change. And so I have on this questions on the model, but since I think this is not the appropriate format to stop for questions. Okay, so now I'm going to talk about measuring orbitals. And many of you have taken chemistry, and most chemists will argue that orbitals are intrinsically unmeasurable. And I want to put it out right first right out here, and you can think about it as we go forward. But I want you to think about it and think about whether a electron is measurable. You can see why they might say not. There's no such thing as an electron in a given orbital. Electrons are all identical. They can interchange with each other. So there's no such thing as an electron in an orbital. So chemists largely think of orbitals as fictitious and useful maybe for thinking, useful for designing chemical reactions, but don't try to measure it. It's not real. It's not real. It's just something that's helpful. Others argue that wave functions can't be measured, only their squares. And what I'm going to show you is using only experimental data and a mathematical algorithm, we get something close to an orbital. So you can look at it, you can think about it, and think about your criticisms, and I'll try to prepare it and fight them back at the question period. Okay, so let me start out with an artist perspective on how this works. So now I think you're all brought up to speed on the basic ideas of attosecond pulses, and you know that I have an original wave function, and I peel a little bit off, creating a wave packet. I drive the wave packet back, and I let it interfere, creating the radiation. So here's an illustration, an artist's illustration of the electron. Remember, it's chirped, and so you see the chirp in it going from red to green to blue, just like I told you. And you can think about that interference. I'll let you think about it in your mind. This is an illustration of a nitrogen orbital. So plus minus plus. It has a different phase like that, and the atoms are essentially here and here. And you'll find this in any chemistry textbook of the structure of the nitrogen orbital. Think of the interference. Think of the interference when it was overlapping the red part. Think about the interference when it's overlapping the blue part. And just think of how that interference is going to change. And it's really that interference that tells us about the structure of the orbital. Now let's take the molecule that was now like this and flip it through 90 degrees. And now think of the interference. Now I got plus, minus, plus in the vertical direction. And the interference is going to be very, very different, one from the other. And all angles in between, it will be different. And so I want to look at that, and I'm going to use that difference in the structure of the light that's created in order to say something about the orbital. Okay, so the experiment is nitrogen molecules shot out of a supersonic jet. So they're not too warm. Hopefully they're quite cool, about 20 degrees Kelvin. They won't be fully cooled. It would even be cooler if we come down further, but we need a reasonable density of molecules in order to produce harmonics. We'll take a pump pulse that's small in size, that's the orange one. It will be focused, therefore, weakly to large in size here. So we align all molecules. Maybe I should make it clear why the alignment works. Think of this as the molecules, and I have a laser field pointing up and down, and I'm pulling the electrons, and I give it a little twist this way when the field is pointing this way. But as the field changes, the electrons internally sort of bias, the other way, and it still pulls it towards alignment. And so molecules are pulled towards an alignment with an intense laser field, creating a rotational wave packet, a bit like a pendulum. And all pendula align, and as long as the angle is not too great, align at a certain time delay afterwards, and molecules are no different. So I made sure I turn off my laser pulse by the time they're aligned, and then they're just going to go through this kind of quantum mechanical process again and be aligned again. So I'm going to pick one of the revivals later on when all the molecules are aligned. And I'm going to bring in the second pulse, a probe pulse. It's shorter, more intense, and its purpose is to ionize and create high harmonic radiation. And the high harmonic radiation, we're going to look in a microchannel plate. And I think I told you about that. So it's going to be much the same as what I've described to you already. So here's the normalized harmonic intensities. Harmonic number along here, that is the wavelength of the electron, essentially. Harmonic number along here, harmonic intensity in the vertical direction. From nitrogen of different alignments. And here's the alignments. You can see that there's a whole set of them, 5-degree intervals. And it's really not important for you to see the details of this. Just look at the big difference in the structure of the harmonic spectrum as we move from one side to the other. The illustration is down here in the bottom. And just look at the harmonic, just a big, big difference. I mean, how could it have been any other thing? So there's the basic raw data, and then one can reconstruct the N2 nitrogen orbital from this data. I'm sorry, I didn't realize this was overlapped, or I would have fixed it. You can reconstruct the nitrogen orbital from this data. There's a couple of assumptions. We assume that the recolliding electron is a plane wave, but of course it's coming into an ion, and so it's modified, but we keep the plane wave approximation that allows us to use tomography and reconstruct it via tomography. We make assumptions on phase jumps, but those have since been measured. And so this is the reconstructed orbital of the nitrogen. Here's a calculated by multi-electron calculations and filtered by the spectrum that we have to look at it with. And this might be what you might find in a textbook. So we reconstruct from 19 angular projections using tomographic methods. It's the wave function, not the wave function squared. Of course, it's all relative, so we only know the relative phase between these parts. There's no such thing as an absolute phase. So taking stock, and then I've got a few more minutes left, and I'll end up with the next example. The experiment constructs a superposition of the n-electron molecular wave function with the n-1 molecular wave function plus the continuum electron. We measure the difference between the n and the n-1 molecular wave function, and that's the Dyson orbital. So we measure a Dyson orbital. Okay, now I've said, can we make similar measurements of wave packets to what we do with optics? And I've shown you the possibility of looking at the static electron, but of course, attoseconds is about dynamics. And so I want to tell you about something we're working on now. The other was an older work. I want to tell you about something we're working on now. And maybe I'll put it in a context. So there was a paper published in 2005 by Cederbaum's group. That's from the PhysRev letters, you can see the material. I've got, my part is overlapped with pictures, but I think you can see it all. So it's the universal attosecond response to the removal of an electron by Cederberg's group. And basically what he says is that if you remove an electron instantly, other charges will flow in. He doesn't say it in these words, but other charges will flow in, and the natural time response, which you can hardly overcome, is about 30 attoseconds. So this seems like something that's really important to measure. We should go after it. I like to think of it as the plasma response. So this is the formula for the plasma frequency. And you can look at density of electrons as a function of position. And really what he's sort of assuming, I think, in all the examples he's assuming, are that, there are sort of 10 electrons per average atom in almost any molecule you can think of. You can think of really extreme molecules like I2 or something, and it may be different. But even those are larger apart, and so the density is not so much higher, not as high as you might think. But if you take an average one, it turns out that the density of electrons, I think, is about 2 times 10 to the 25 per cubic centimeter. And the natural plasma response is about 30 attoseconds. As I said, that's my words, not his words. But I think that's sort of a typical response. And it's not so easy to go beyond that in ordinary matter. So if there is anything like a universal attosecond response, we should look at it. So how would you go about looking at it? There's really 2 ways. One has been developed in photoionization before, and it's a lot of work being done now in Attosecond Science using photoionization. And I like to look at it from the point of view of a xenon atom. If you were to photoionize a xenon atom, try to do Cedar-Bon's experiment, remove an electron as fast as possible, off goes the electron. But that electron provides a field that all the other electrons must respond to, and their response provides a force back on this first electron. And so the multi-electron response is encoded in the photoionization, the characteristics of photoionization, and particularly the spectral phase. That is the phase of the photoelectron as a function of its energy. But there's a second way. Nobody does it, but there's a second way you could do this experiment. You could do a photoionization, a attosecond pulse experiment. You tunnel an electron out comes the electron. You drive it back in high energy, going to create an attosecond pulse. As it approaches, other electrons feel the field. They respond to it. They move away. There's a force placed on the electron, and this electron is modified, and that is written in the spectral phase of the recombining electron. And we can look for that. In one case, it's written on the recombining electron only. In the second case, you have to assume that you remove the electron very rapidly. And that's not always the case. In different molecules and complicated molecules, the electron can be trapped and move around, and there can be all kinds of delays and phases, spectral phases introduced by the structure, especially of molecules. And these are going to be kind of mixed up in this measurement, and they are. Where in this case, since we're going to measure, I'm going to show you that we can measure only the recombining electron and not worry at all about this kind of stuff going on in the atom. This might be a preferable way. So there are 2 approaches. I'm just going to repeat it. One is to use streaking, which I already told you how that works, to look at the photoelectron spectral phase. And whatever distorts the electron replica, whatever it distorts is included. Another approach is the interferometric approach, which I'm going to now talk about. And there I'm going to measure the spectral phase only of the recollision electron before recombination. And I probably don't have a lot of time, but I don't need a lot of time for the last of this. So our approach is always an interferometric approach. So let's produce an attosecond pulse with 1 beam. I told you how you can make a very short pulse, only about a cycle or so, to create an attosecond pulse. You can be a little more sloppy by using a slightly different approach, a time-dependent electric field. This pulse starts circular. The electron never comes back if you follow F equals ma, and it goes linear, and there it collides, and goes back circular again. And that allows you to be a little more sloppy. You can have a little longer pulse if you make it in this more complex way. And that's what we do in my lab. And then you come in and perturb that with the second beam, like an interferometer. An interferometer, you have two paths, and then one arm, you're going to perturb, you're going to have a little micrometer, and you're going to move one arm relative to the other. And this one, this perturbing beam, is really the interferometer, is the micrometer, essentially, that you use in an interferometer. These two beams interfere in the medium, creating a diffracting beam. If you think about the electron, it moves along the strong field, and so the weak field is really creating a little phase and amplitude grading on top of this really strong one. And because the electron is moving along the strong one, there is a delay as you move up and down, and so it really is a phase and an amplitude grading that's written. Now you're going to remember that different colors return at different fields at different times. And so a phase and an amplitude grading will have encoded in it information about when the color returned. So out it comes, a diffracted beam. It's picked up in a toroidal mirror and focused back down on the screen over here. In between, we have a physical grading, which separates the colors. And so there will be red, green, and blue. And we're going to look at the structure of that grading in here as seen by the red, green, and blue radiation. And that will contain information about the details of that electron in that interference process. Such a measurement. This actually doesn't go all the way up to the shortest wavelength that we need, but we can go up to it. And I like to use this because it's a nice illustration. You can see the curvature or the difference. So first, this is the grading that's played. It's a normalized difference to allow for the fact that I have a Gaussian beam. And so there's less energy out here than there is in the center. And so we normalize it, make a normalized difference. And then we look around the center and we follow a line of constant intensity, or you could follow the maximum in either of these. And you can see the curve, the movement of the grading up and down because of the different return time of the electron for different colors. And we can trace that if we push the extreme even further and look at it, and we see the added chirp that you normally expect. That's the chirp I described to you from red to green to blue in the very first figure. You can see a deviation from the added chirp, both up and then back down again. And that is the difference in the spectral phase because of the recollision electron. And that has encoded in it all the information about the time structure of the multi-electron response. Okay, we've been looking at this both experimentally and theoretically. So this is the amplitude and phase again that I showed you before. And here is the amplitude structure going from 0 up to 200. It's one's theory and one's experiment. Of course, the experiment ran out of energy at about 95 eV, so it's in here. And so there was a natural fall off in energy there. So that's the peak that's here. So that's the amplitude, and the phase structure is here. Phase structure, again, goes up, back down again, and then we run out of energy in here. So we don't know what happens beyond that. So this is work in progress, but we believe we have a general approach for measuring multi-electron response in atoms. We believe we can push it to molecules, and I dream that we can push it to solids where multi-electron physics is really, really important. But that's a dream yet. That's not reality. So let me conclude. Two beams parallelly polarized isolate any process that is controlled by the recollision electron spectral phase. We have the technology to measure, I think, the universal time response of matter. With photoionization streaking, we can add and therefore isolate the transition moment. So we have everything in photoionization, and we have the universal time response of matter, the multi-electron part, isolated. And therefore, the difference is the transition moment, the phase of the transition moment. So I believe we can measure that. Exciting a molecule allows multi-electron dynamics to be controlled. I haven't made the case here, but it will do so. And correlated electrons are important in quantum materials. And so, as I said, we have a dream, but we don't know yet whether that dream is realistic, that we can apply it to solids. And my final summary, I've described to you Attosecond Science from its beginning to where we are right now. And so let me stand back. We've extended the 50-year tradition of ultra-fast science. We've improved the time resolution of experiments by more than 2 orders of magnitude with Attosecond Science. It's a big achievement, and we as a field have managed to do that. This is the forefront of measurements. We've extended the 50-year tradition of nonlinear optics. We've extended it in atoms, but it turns out to be also extended in molecules, and it turns out also to be extended in solids. And actually, experiments in my lab right now indicate that probably, maybe not a recollision process, but some analogous process is taking place in metals. And we build in the 100-year tradition of X-ray laser science. We integrate X-rays and laser physics, thereby extending the spectral reach of laser spectroscopy, I would say by 2 orders of magnitude. So thank you very much. And of course, I don't do all of this work myself. This is all done within the Jazz Lab at NRC, or NRC and University of Ottawa. And this is, well, a modern picture of the Jazz Lab taken on Zoom. And I wanted to highlight, I've highlighted them before, but Dong-Hyuk Ko, Graham Brown, Chunmai Zhang, who worked on the last part of this, the multi-electron dynamics. Thank you very much.
Great, thanks, Paul.